So I'd like to say hello and introduce myself and Ira. My name is Anna Margolis. I am the founder of Engaging My Circles. I started the program or the school to mainly out of wanting to teach my kids in ways that are engaging and fun. I am a mathematician from for from not from birth but almost. My parents are mathematicians, my grandparents are mathematicians. I grew up in a home where math is almost religion. And so when I studied math myself and then graduated, it was almost really obvious for me. I want to teach my kids math, but I wanted to find ways that are um, fun for them, and I started exploring those. So today's workshop theme is how to play math games with your kids and how to teach math through games. Um, so the first thing that I want to touch upon, even before we talk about games, is uh, or not just my general philosophy that I really love, and we are using when we teach math in EMC, is teaching by asking questions. And any game is usually adventure and exploration of things we don't know. Otherwise, it's not as fun as interesting. So um, I'd like to open kind of an open discussion of why, or what is it, why do we ask, why is it better to ask questions when we teach or when we play or when we do anything with our kids? Why wouldn't we just tell everything we know and let them listen, remember, and do what we say? So originally I wrote down all the key points, but then I thought, how about I just ask a question and see what you guys think, so we can see how much better is it when we have a conversation. If a question is asked, people can say what they think. So how about give me some ideas of why would I ask a question instead of telling you? Why is it good to teach with asking questions? What do you think? Anyone just unmute and volunteer if you have ideas. What can asking a question bring to the table when you're talking to your teaching?
I think it forces the children to think of their own ways of finding a solution, of solving a problem. It's not just a passive learning, it's a more active learning.
Okay, anyone else?
Increases curiosity.
Curiosity, I like it. Right, because we ask a question and then we start thinking right away and we become curious. I believe if we ask a question and it's not a question we know the answer to, we want to know something we don't know, so something new. Um,
For me, it was always a way to actually make sure that people are paying attention, because when you ask a question and you're actually activating your brain, just simply listening, because you need to answer something specific. So
just put attention.
It's also because children sometimes surprise us with creative ways of thinking.
Yes, not something we already know. They have their own ways that we didn't think about, and we don't want to spoil those. Anybody else? I also really like when I ask a child a question, and if this question is at the right level that he can answer, he will feel that he did it, not he himself, and uh, I can congratulate or acknowledge his achievement, his discovery, and he will be the owner of it. And that's the main thing. That's the the win on his side. That's not something that something he accomplished himself. Uh, so that's one of the um, big benefits of asking a question, letting the kid uh, think and discover. Um, how about how do you feel when you are asked a question and you don't know the answer? Is it good? Is it bad?
Insecure.
Is it some insecure, right? So if we ask the right questions, and that's actually, I think it's actually good to not to experience this insecurity when you don't know the answer, because if I ask you questions that you know answers for you're not really learning anything new. But to learn, we need to learn how to not know and how to go through that. So if we don't set up our learning environment to teach us how to face questions we don't know and to experience this insecurity and think through it and struggle through it, I believe learning is not happening for real, for us to become independent learners eventually. So when we ask a question, we create this uncertainty, unknown things that we might be struggling through, or our kids are going to be struggling through. And then if we give enough hints, and they will struggle through, but get through it and find the answers eventually, and experience this um, success that they own and they deserve. So that's how I like to teach. I like to ask a question and see what they come up with for the answer. And I really also like one more thing. When I ask a question, there might be a right answer, but there also might be a wrong one. And mistakes are huge stepping stones for us to learn from. So wrong answers are amazing ones to look for why they're wrong and what is the correct way to answer your question. So that's a couple of more on my ideas of why asking questions is the right way to teach. So then one more thing, why play? I have this short because it's fun. Why else? Any ideas? What
Allows
benefits?
for creativity.
Creativity, okay. Um, what else?
Maybe to tap onto what you were saying before, when you're wrong, it kind of allows you to be wrong in an easy way, kind of a playful way, not to be afraid, just to try new things.
Oh,
Yeah, the stakes are not high. Like it's not a test, right? The consequences aren't too bad.
it's not real life. It's a pretend environment where we can safely, yeah, the stakes are not high. Okay, anything else? What about why do you want to play? What about motivation? I
It's just fun way to interact with the world and people.
oh, we are not alone. We have friends. It's more fun together. Now I'm a bit dyslexic and English is not my first language, so get ready to look for mistakes in how I type and write things. um, I also really like games myself because of variety of different um, setups um, or scenarios where we can do things in different ways for the same type of skill. So we don't get bored in games because we can do something else every time. So it's just variety. Um, any other ideas that come to your heads before I spill out mine? So another thing I really like in games that we have a lot of tangible, touchable things to use to play with, and these things usually help to take abstract concepts and make them actual things, actual tactile and experiences that we can connect and understand and feel through hands. So another thing that again I can think about is when we play games, we can create imaginative words, and we if we learn through playing games, our learning becomes some type of story, some type of adventure, or at least we can make it so. And this develops our imagination, our problem-solving skills, um, our ways of thinking about any type of situations, the ones that we find in games or the ones that we later find in real life. Um, and last thing is, again, we said it, it's more fun to do things together. Usually games involve more than one player, even though there are games that involve just one player, the solitaire, like Sudoku puzzles or many of this kind. But when we play in a group of people, we develop very important social skills of how to talk to people, how to teamwork, how to collaborate, how to lead things. So that's another benefit of playing games. And never mind math, is just any game you play uh, will get us there. Um, so well, let's go to some games involving math, of course, because that's what we are teaching. So I want to start with actually a trick, um, which is not really a game, but it's something that we can use it's a playful way to show the magic of math, and math has a lot of magic behind it. So I want to ask, before I start this trick, if anybody knows it. It's a trick of calculating the sum of the numbers that hide on the dice by looking just on the top number. And by by numbers that hide, I mean, if I stack, if you guys see here, I'm stacking, let's say 4 or 3 dice all together, there are all around numbers that I can see if I walk around this stack of dice. And there are a few numbers that I can't. So how many numbers I can't see in this stack of dice? So anybody can answer?
8.
8. How do you get 8? So let's count, Lisa. Between we make here. Well, how do you count 8? It's close. There is another 9. Okay, I'll put 8, 9. And I might be mistaking myself. So the ones I don't see are positioned between each 2 dice. So I have here dice number 1, dice number 2, dice number 3, and dice number 4. in between 1 and 2, how many numbers I don't see?
2.
2. So I have 2 here. In between 2 and 3, I have another 2, right? In between 3 and 4, another 2. And there is last number I don't see. Where is it located?
Bottom?
On the bottom, yeah. If you can read the answers people are typing in, because it's
Yep.
easier for me. Yep,
9.
on the bottom.
Catherine wrote
So
9.
so I think, let's see. So there is 2 in between the first and the second, 2 in between the second and the third, 2 in between the third and the fourth, and 1 more on the bottom. All around, if you imagine me walking around this and looking at this pile, all other numbers I can see. So there is 2, 2, 2, 6, 7 numbers I can see. So anybody's familiar with this trick? I will be able to tell you what these 7 numbers add up to. Right? It's a no. Good. Okay, so I'm gonna switch the view from this shared to Irina's screen so we can see it a little bit better. I asked Irina to prepare a pile of dice. She has 4. Now, I don't know how she set them up. I don't know what numbers are hiding. I would say that. But I will ask Irina to show me just one number, the one that's on the top.
Okay.
And I don't care about the rest. I will be able to say how much she has how much all other numbers add up to. So Ira shows me 1.
Yep.
The rest of the numbers add up to 27. Now let's see how I do this trick. What is my magic? By trying, I will be telling you what I do, and you can try to guess why this works. But first, let's see if I'm right. So anyone is especially good at addition and wants to volunteer, add up the numbers to see if I'm right, if there is 27 hiding?
My husband always telling that I am the number person. I mean, I can volunteer if nobody else volunteers, but I can try to be the number person too.
Okay, yeah, add them up, but show us what you're adding.
Okay. 6
Okay,
plus 3.
9.
9. Thank you.
Wait, you have 1 on
Yep.
the other side of 3.
Yep.
Mhm.
I have 4.
Okay,
Okay,
9
13.
and 4. Okay.
And then 2, 16.
Mm-hmm.
And then 5, 21. And then 3, 2, 23.
Mm-hmm.
And then 5, and you were correct, 27.
Wait.
No?
You
Yeah,
20,
27. You said 27.
23, and I said 27.
Yeah.
But we had a mistake in the middle. You had 23 before?
Yeah.
Let's check. 5.
Okay, let's see. I had, this is the last one, 5.
Let's go from the 5 and 3. Yeah.
5 and 2, not 3.
And 2. Mm-hmm.
Mm-hmm.
7.
7. 2 and 5 again.
That's another 7.
Mm-hmm.
Mm-hmm. 14.
Then 3 and 4. 7.
Mm-hmm.
And 6.
And 6. Okay. So I was right. 7,
Yes.
7, 7, 21, and 6, 28, 27.
Yep.
Okay.
You want to do another
So
one?
let's do another one, hide them. And now why is this good to do this trick with the kids? Because you're doing a trick and they're checking your math and they're doing addition just to figure out how you're doing this trick. Okay. So let's set them up. We don't see what Ira is setting up.
Mm-hmm.
Okay. But let's ask her to show us just the top one. That's 4. While we checked the trick, I gave out a little bit of how it works. Anybody got it, maybe? Anybody has a guess to what the numbers in between the cubes will add up? Not yet. Okay, so it's 24. Let's check.
Wow. Okay.
And we're gonna add again. So we're gonna practice addition to check my magic skills. So 3.
3.
And now let's practice it in a way I'm gonna try to how do you say, to give out the trick to you guys. So try to notice, what am I doing? How do I know it's 24 right after I saw 4 on the top? So there was 3. And maybe I'll start sharing and making notes of what we're doing.
Yep.
Um,
And hi to Jackson that joined us.
so
this
there
is
was
2.
3.
Mm-hmm.
There's 2. Okay.
Okay. And there is 5 on the other side.
1, 5. Okay.
So 10 altogether. Then there is 3.
Then there is 3. Okay.
And there is 4. So 7. So 17. And there is 6, meaning 23, plus 1, which gives us the correct answer, 24, that you guessed. How did you do that? I'm very curious.
Okay. So what are we noticing? Because I don't want to do it. So with your kids, you can do the trick after you know how it works, as long as they are not losing their patience and don't want to give up on trying to discover how it works. But now that we've added so many times and we see that I know magically to without spending any time on adding these numbers, right? I tell you the answer right away. First time was 28, second time is 24. I'll give you another little detail. Ira may even not set up the cubes, just show me the top number. Let's see how it connects. So maybe let's write some patterns. So when I saw 1, I said it's 27, right?
Yes.
When I saw 4, I said it's 24. When I didn't see, but Ira, you can give me one more option for the cube.
Sure.
Okay, or let's go over all options. Let's see what can be on top of the cube. How much is it? I can see it's too little for me. Oh, you're muted. Unmute? Ira, you're muted. Oh, there.
Yes, 6.
Is 6? Okay.
Yep.
If you show me 6, I'm gonna say it's 21. Okay. Anybody notices a pattern in these numbers? 1, I say 27. 4, I say 24. 6, I say 21.
Totals are declining by 3 in this particular list.
They are, but if I go out of order and put 3 here, that's because my and that's gonna be 25. Now it goes up. So try to look for connection between 1 and 27, 4 and 24, 6 and 21, 3 and 25 in all of them. Is there anything in common to 1 and 27 as well as 4 and 24, as well as 6 and 21? Same property. 3 and 25 have the same. Try using addition.
Shouldn't it be 6 and 22?
6 and 22, correct? There we go, mistake. So, okay. So who was it, Lisa?
That was me, Anya.
Anya. Yeah, 6 and 22. Okay. So I think Anya got the connection. Anya, what's the connection?
They all add up to 28,
They do.
which is, yeah.
So now if you guys see, if you pile a cube, four cubes, and you see, let's say 5 on the top, what's going to be the sum of all the rest of the numbers we don't see?
23.
We can check that theory. Do you know why? Cubes are very, very specially built. Now I have here a little spoiler of some connections with these orange and red and green arrow. What's happening on each cube when we were adding to opposite sides of the pile? Why is it really doesn't matter how Ira piles the cubes? Ira, can you look at your yellow cube? What are the two numbers that are hiding on top and the bottom?
4 and 3, they're combining 7, all of them combining 7.
Yes. So if I stack 3 cubes, how much do I have total on those 3 cubes covered that I don't see?
21.
21, 7 times 3. And then I have one more in the top that combines 7. Which part I see? The top part I see, and the missing one I don't. So
you subtract. Oh, that's so smart.
so 4 cubes would hide how much if you cover all the top and the bottoms, right? If you cover the top one and don't look at it, 4 cubes would hide 28. And then you uncover, or you look at the top, or you show me the top, and I just do 28 minus 1 and see what's left, 27. So it's an example of some math property that we took, and without saying how it works, because I could just tell you step by step, we played it, we asked questions, and you guys discovered what's the mechanism. And if you're a kid, you did a lot of work on the way to this discovery. So I'm happy you weren't sitting and doing worksheets for me. You were doing this mental addition and subtraction all the way through. And hopefully it was fun. So let's go to now some games that we can actually play. And I will start with games for young ages. I call this type of games catch the thief. So normally, I have some pictures here with the setting with dominoes, but you can play with games setting up with any type of number roads, playing cards, 10 frame cards, dominoes, any objects that you are going to steal, and your child is going to try to discover what you stole, try to guess what is missing. And here is the mystery that they're trying to solve while they're playing the game. And the learning component of this game is the setup. To start playing the game, you can use the time of setup the game to teach. So for instance, you can teach number decompositions or number families by asking the kids arranging dominoes or parking the dominoes, I call them, into their number slots. So making these exercises of addition, subtraction, or combination of numbers. So before they start playing the thief. So I'll get back to it in a second, but first we arrange some objects in some certain way, and arranging them in such a way we are learning a concept. And then we, after arrangement is done, we start playing thief. I like to tell kids a story where they go to sleep, they close their eyes, they go under tables, and a thief comes to their house and steals some of their toys. As soon as nighttime is over, they wake up and they need to catch the thief by telling me what was stolen, what's missing, and how do we bring um, the home back to order, or the setup, the original setup, back to how it was made. So one setup is take dominoes. Everybody has dominoes. Ask your kids to imagine you have a parking lot, uh, place some numbers, write them down, or just group the dominoes by, of course, the uh, number of dots that they add up to. And that's a really good way to go over all possible combination of breaking numbers into parts. I have some examples here of the only two ways of making three and zero, two and one, the only two ways of making four, and we can keep parking the dominoes. I don't know, 5 and 6 is gonna go to 11, and by the time we end up parking the dominoes, we counted them, we went through all options to uh, make all numbers as a sum of two smaller ones. Uh, and after we park the dominoes, we start playing the thief. So you guys close the eyes, go to sleep, and I steal a certain combination of numbers. I'll skip the dominoes and we'll play this game with some other objects, uh, mm, because it's gonna be long to arrange them in a way. Um, but let's see what else you can use with the same dynamics. So I really like, I don't know if you're familiar with the Questionary Roads. These are number rods that don't have any number written on them or points. The only thing that identify the rods with the numbers is uh, their different lengths. So when I introduce the rods to the kids, I like to ask them a question. Why do you think these rods are numbers? How can I tell which one is which? And of course, what would be the answer? How would you guys figure out which one is which? You have these rods, they're all different lengths. Why are they numbers? Who is number one? What can you do to figure out which one is which? Any guesses what could be number one? Which color?
The white one?
Yes, it was the smallest one. Which one is number two? Have some. Yeah, well, let's assume this, Catherine, let's assume these numbers are whole numbers for now. And yeah, the white one is the one. Then how do I know which one is two? So if I were a kid and these were at my fingertips, I would start trying arranging them in some order, and pretty fast I would see, right, which one is which, and would make some type of order, and see 1, 2, 3, 4, 5 up to how much which one is 10. Oh, I'll spoil it for us. So the orange is 10, or here I built a little or a bigger staircase of all these numbers going through from 1 to 20. And if you arrange them, of course, by just counting, you can figure out which one is which. So Catherine is texting, so I'll read your response.
No, I was just saying that, yeah, no, so my son actually does he has independently come up with a version of this where he'll just take his regular blocks and they have different sizes. And so he'll assign like a value of 4 to this size block, and a block that will be twice the height will be 8. And then one that would be, twice the value of the 8, like the height of the 8 block would be 16. And then he'll assemble them and calculate the total value of this. And then on different days, he'll decide that the block that was 4 yesterday is all of a sudden 3. And he's actually started doing fractions, and he's just 5, and it's totally come from him. It wasn't even a game I suggested. He invented it.
And that's exactly example where you just give a child blocks and maybe say what is it, and they start figuring out their own ways of making them numbers or parts, and really working through the numbers. You don't need to explain much because they have in their hands an object that explains it for themselves, and they just give it the correct meaning. And there is no one meaning. You can do different things. You can do fractions. You can start giving them values of decide this is a 2, and then the red one will be a 4. And then, like your son did, I actually have never thought about using these rods this way. So yeah, we can give them, we can count by 5s now. If 1 is 5, and you're going to be doing 5, 10, and 15. So many things come out of this freedom of what do you think about what this can be. But I really like the physical manipulative, because now I don't need to explain what 11 is. It has a 10 and a 1. I don't need to teach what a 20 is. They just touch it, they see it, and they know it. And I really, Catherine, I am very grateful for sharing your son's idea, because now I have a new teaching tool. Now we're gonna do multiplication with rods as well, because this is gonna be 5, 7, or whatever, right? And I'll be asking, if this is a 7, how much is the next one? How much is the last one? Okay, I have what's in the 10th place. How many of these fit in? And that's a cool visual. So again, if we go back a little bit for the little ones, the K's and ones, I like to make stories as soon as you have physical construction. And here I see a staircase. I like to ask them, go up the staircase, go down the staircase, jump over. And when the thief comes, he can steal things from them, and either at night or either as they go, a little bit slow. And here you have a staircase. No longer we obviously see which number is which, and we need to do some subtraction or skipping numbers to be able to come down the staircase successfully. So you guys can try. It's not so easy, right? If you are standing now on the top of the staircase, and a thief came to your house, and you can only catch him if you successfully jump over the holes. You need to tell me the numbers you're jumping over, or the numbers you're jumping on, or the numbers that are missing. Okay. And as soon as you are done it, I can return and give you back your toys. So kids usually really like it. I am not gonna ask you to do this exercise. I think you guys will be successful. I wish we had kids in the in the crowd.
Next time.
Yes, but that's one way of playing with the rods. Another thing that Catherine said, and I really like using these rods for, and again, you can play the game in the middle of your, I would say, sessions when you teach something, and then when we get tired, we can start stealing from each other and guessing what we stole, or in the end as a reward, because we learned some concepts and we decided some things, and it took a long time and we got tired. So Catherine said her son was adding up the numbers he assigned to the rods and combining them. So the Questionary roads are a great way of calculating Gauss sums or addition of a lot of numbers in a very, very clever way. So I don't know, this I want to ask parents. Maybe there's somebody who doesn't know. What if I asked you to add 1 and 2 and 3? All these steps, they go up to what do they go up to? 220. How much does this add up to? What is 1 plus 2 plus 3 plus 20? And so on. Yes, the 3 dots mean I'm adding 4 and 5 and 6 and 7, all these step shapes. Right. There is a name for, or it's not my invention here. You can add up different step shapes because they are a pattern. So what do they add up to? We'll go, as since we are big and adults, the first 20 numbers. It's a classical arithmetic sum formula. And okay, and if we are big kids, what if I put 100 here? Okay, but let's do it 20 and then we'll generalize 100. Anybody can tell me really fast, or find a way to tell me fast? Be a kid, what would you do? And you don't want to add 1 and 2 and 3 in this order. Any ideas? 200 is close. I remember this answer. I remember the cubes. I always figure out this 200 is very close. Catherine, why 200? Why is the guess?
No, I know 1 plus 2 to 9 is 45. So I was just trying to do the rest quickly, but
we could do what you just did. This is a 45, right? And then you did the another 45 probably somewhere else.
I did not, but now that I see the rods, it makes absolute sense.
And then you would have some nice stands left over.
Mm-hmm.
But you could also, without counting the 45, what could you do with these two?
Well, you combine the 1 and the 9 and the 2 and the 8.
You can basically.
I forgot a 10 somewhere. Or
Ravish 190 is close. Let's do 100. So let's see how many. Catherine just combine the 1 and 9. Right. They're combined by number
90.
1 and talk about how to make sense.
Oh.
Or do this.
So 45 plus 45.
45 plus 45. What do you think?
90.
I'm gonna create. Yeah.
Anishka, for some reason we're hearing an echo.
Okay.
There we go. I can do it like this without even going one by one, right? And then 200 was amazing, right? Where do I have 200? Because from 1 to 10, this was 10 things. Under it was 10 things. So I have 200 and then a little bit more. So the answer is 210. right? So I just really, really love those roads because of this property. This is exactly how we, yes, n times n minus 1/2. That's the algebraic one. Where I wish do we have n times n minus 1? The actually this way we didn't do n. I would do n plus 1. N plus 1 times n/2 for the correct formula, right? But that's n times n minus 1/2 is not gonna be 210. And here in my picture, I didn't do, yeah, 10 minutes left. Oh my God. Okay. So I'll skip the formula. I do want to go over, we are only done one game. So I do want to go over a little bit more settings. So for, again, with this Questionary Roads, you can talk about how to make 10. You can make houses of numbers, and how to make 9 and how to make 8. Again, same idea as the dominoes. You make the numbers, then you steal some floors from your homes, and you ask the kid what's missing, what makes 6, 1 and 5, what makes 8, 1 and 7. He can be a thief and ask you what he stole, and that's also very fun. So in the very little time that's left, I want to show another game dynamic. It's very, very similar to a set game or a spotted game. And you can play it with cards, or I like playing it with cards, or with, you can play it with dominoes, anything that has numerical values on top of it, and you have a lot of those things. So another type of my favorite cards, like the blocks here, were my favorite type of manipulative for visualizing addition, subtraction. Another favorite type of manipulative is the 10 frame cards. So I want to show how we can play a game that's called IC10, but you can actually play a game of IC12, IC21, IC any number you want to practice addition up to that number. Okay, so my original cards have values 1 through 10. They are here. And now I'm going to hide them, simulating a gameplay where you are dealing cards into the middle of the table, one at a time, or it can be 4 players having their own piles, and they are flipping each one their own card, and you have 4 cards on the table. So here we go. I only ask a question as I deal a card. Do you see 10? Can somebody answer?
No.
No. Let's say we dealt 4 players, dealt 4 cards. So I just randomly put 4 cards. Do you see 10?
Yes.
Yes. Lisa, where?
1 and 9.
1 and 9. And Lisa get the 1 and 9 because she saw 10. You can play it competitively. So means whoever says first yes shows me 10, gets these cards into their pile on the side. At the end of the game, we count how many 10s who has more. So we also count by 10s at the end to score our points. And you continue like this. So as soon as there is empty space, we either flip more cards on the table altogether, or we just add the missing ones. And again, we ask, do you see 10? And here we have a yes, I think.
Yes. 2 and 8.
And Ira gets 2 and 8. A little bit better scenario. I'm gonna a little bit more complex scenario I think, do you see 10 now?
Yes, 1, 2, 3, and 7.
Yeah, 1, 1, 2, and 7. So it doesn't have to be just 2 cards. It can be any number of cards as long as it adds up to 10.
So a little bit
Or
different than sets then, in that sense.
yes, well, sets is more complicated. Here you only need to practice. You only practice addition, but it's very fun. We played this game in. Here you see kids are playing by themselves, so they're playing in pairs, and each one is flipping some number of cards, and then they're looking for 10. And whoever grabs it first. Um, Here we are playing in a collaborative setting where a teacher, or I think here we are already counting the points, but a teacher would have a setting and kids would just go in turns. So I like to add a rule where we all can see 10. So we all say yes if we see. And every time there is another child that needs to find the 10. So that way you kind of go with their urge of, yes, I see it, but you give them a chance to give a friend a turn to find, because you can say, I see, but you will be waiting for the next friend to find it. And you're giving a hint to your friend, yes, there is a 10, look for it, good. You can see, I see, you can play, I see a number with the rods as well. So do you see 7? Which one is 7? You can count. Then 7 is black, right? I'll just go here. But if I have this setting, for instance, which practices the number steps, I can say, I see another 7. Where is another 7?
You're pointing on it?
No,
No,
I
not
found,
necessarily.
oh, well, there is this black 7, there is this black 7, there is this black 7, but where is another 7? There is another 7. I see another 7. Where is it?
Can I combine several?
Yes, yes, and you can make another 7 for me. And there is another 7, so the 1 and 6, and again, it's the same story, the 2 and 5, and the 3 and 4. And you can find numbers, not necessarily just 10, using the rods. I really, really like the polyomino cards, and we made them. You can print them out. We have handouts for you to use. I'm not sure if you can buy those. The base 10 cards, the 10 frame cards are very, very classical, and they're on Amazon as set of actual cards set size. The rods are easy to buy and not very necessarily to make, but these I've not seen in any production, so I've made them, and you can just print them on cardboard. That's a different visual of numbers, and the same dynamic here. We don't flip the cards, we use a certain amount of cards that are already there, and my goal to find, I don't know, if we were practicing 10, or if maybe we are practicing just breaking 7 into parts, or a bigger number, my goal is to clear the table of cards, and we will take turns, or whoever is first screams 7 and takes those 7s to his pocket. So I don't know, I would take 2, 4, and 1. And that's my 7. I put it on my side. Ira, take turn, take another 7. It's my 7.
I'll take the 5 bottom, the 5.
5.
Yeah,
Okay.
5. 5 and a 2 on the right. Yeah, you
Okay.
report.
5 and 2.
Yep.
Now later you can count points by how many cards you took, or how many 7s you have. So you can be adding sevens, or you can be just, when you're taking the cards, you can be thinking, how can I make 7 with many numbers? Or how can I, or you can play the game with who has more cards wins, or
less.
who has less cards wins. And then you will be thinking, how can I make 7 with only one? Well, one with these cards you can't, because I made these go up to 5. These are pentominoes at most. But you can perhaps make cards that have more squares in them, and then you can be thinking, well, how many cards do I take to have the least amount of cards possible? And then when all 7s run out, or when all 2 parts run out, you'll have to be taking more parts. Okay, so this is I see a number type of gameplay.